Right, so welcome back. We will continue with assembling our global finite element equations in global matrix vector form, right? And we will do this by using this idea of mesh connectivity, and in particular I'm going to try to use that example that we constructed to illustrate how this proceeds. Okay, so assembly of global matrix vector equations, but really this is the matrix vector weak form. Okay, essentially what happens is that the expression that we had at some point in the previous segment, which is sum over E C E transpose K E D E equals sum over E C E transpose F bar with our redefined forcing function, F bar internal E plus sum E belonging to the set of elements that have one of their faces lying on the Neumann boundary, C E transpose F J E. Right, we have this. Now, this will be replaced, as we know, with a set of global vectors, right, vectors and matrices, which I'm going to write now as follows. I'm going to write this as C transpose K bar D bar equals C transpose F bar internal, okay, plus C E transpose F J, yeah, just Fj. Okay. The reason I've introduced bars here is something you may recognize from our treatment of the one-dimensional problem. We know that we still need to account for the proper handling of Dirichlet boundary conditions, and when that is done, you will recall that the matrix in place of K bar as well as the vector in place of D bar are going to be a little different, right? They'll have different sizes, okay? And it's just to leave us that freedom that I'm calling these K bar now. Okay, let's first look at what K bar itself is. K bar is defined then as through this sort of abstract representation of the assembly over all the elements of the individual element stiffness matrices, right? And likewise, F bar internal is the assembly over elements of F bar internal over each element E. Okay, let's now talk a little about K bar. Okay, so essentially this process of assembly is something that we go through by looking at mesh connectivity and simply putting together the components of K bar by accounting for the local and global degrees of freedom. Okay, so let's suppose we're looking at K bar. Okay, and this will be a big matrix. Let's look in general. Let's suppose we are looking at the contributions to the particular row where row and column, right, corresponding to the A bar degree of freedom. Okay, this is where the A bar degree of freedom arises. Okay, and likewise perhaps here. Okay, right. So what I'm going to give you is a single expression here for all the contributions to the A bar component of the stiffness matrix. Okay, all right. Now what we see is that in terms of the element stiffness matrices, okay, we have contributions from KE1 plus KE2, KE3, KE4, KE5, KE6, I need more room as often, plus KE7 plus KE8. Okay. All right. Now, if you look back at the way we described our global degree of freedom A bar as being related to the local degrees of freedom of elements E1 through E8, okay, what you will note is that in element E1, A bar occupied the 7th local degree of freedom. Okay, so the contribution that comes from that element to the A bar entry here would be KE1 7 7. Okay, for E2 it would be KE bar 8 8. For E3 it would be KE bar 5 5. For E4 it would be 6 6. For E5 it would be 3 3. E4 it would E6 it would be 4 4. E7 it would be 1 1. And E8 it would be 2 2. Okay. Note also that because I'm looking at only the A bar component, right, of the global stiffness matrix, or the global, in this case, conductivity matrix, I'm sorry, we have also the diagonal contributions from each element, right? If instead of looking at the A bar contribution, I were looking at maybe the A bar B bar contribution, right, where B bar was some other global node, okay, all right, then we would have contributions to this A bar B bar component of the global conductivity or global diffusivity matrix, okay, where here we would have in general, maybe I'm going to write just one or two of those contributions, right? Let's suppose that this came from some element EI, okay, all right. Now let's suppose that in element EI, the A bar global degree of freedom corresponded to the local A degree of freedom, and the B bar global degree of freedom corresponded to the local B degree of freedom. okay, in element EI. Then that contribution KAB from element EI, right, from the local conductivity matrix of element EI would show up in the global A bar B bar position. If in a different element A bar and B bar also showed up as local degrees of freedom, let's suppose in element E sub j, okay, and let's suppose here in element EJ the global A bar degree of freedom corresponded to the local C degree of freedom, right, and the global B bar degree of freedom corresponded to the local D degree of freedom. That's where they would show up. Okay, so that would be an off diagonal contribution, okay, from different elements, and of course there could be more elements in here, right, in general contributing to that to the global A bar B bar component of the stiffness matrix. Okay, so this would of course continue, right, and you would essentially populate the entire stiffness matrix by doing this. But note in particular that once you have the mesh connectivity information and you have the conductivity, the local element conductivity matrix for each element, it's actually a fairly simple matter to slot them into their global positions in the global conductivity matrix. Okay, all right. And essentially the same sort of approach holds for the F bar internal and also the FJ. Okay, all right, so let's just complete that that bit of assembly as well. Okay, so essentially likewise, right, let's suppose I'm looking at F bar internal, the global matrix, sorry, the global vector. Okay, it'll be this great long vector, right, because it has all the global degrees of freedom in it. And for essentially for the same sort of situation that we had, let's suppose that we were looking again at the A bar contribution to this, right, and the A bar would show up maybe somewhere along here. Okay, so now this would be fairly straightforward. What we would do is we would look at F bar internal from elements E1 E2 All right. Okay, and now this is fairly straightforward, right? For element E1, we know that the global A bar degree of freedom corresponded to the 7th local degree of freedom. For E2, it was the 8th. For E3, it was the 5th. For E4, it was the 6th. E5, 3rd. E6, 4th. E7, 1st. And E8, 2nd. Okay, so that's how things would add up, right? And of course, for any other global degree of freedom, for B bar, actually, if I just continue with the sort of approach that we'd used previously, what we for the global conductivity matrix, this is what we would get. We would get F bar EI B plus F bar EJ D. Okay, right? And this would be because we concluded that, or rather we set it up such that the B bar global degree of freedom corresponds in element EI to the B local degree of freedom, and in element EJ to the D local degree of freedom. Okay, and you would do the same thing for all the other entries, right? And essentially the same thing with F bar, sorry, not F bar here. Essentially the same thing with our Fj global vector, which represents the contributions from the tractions. Okay, right? If again, let's just do it for B, for global degree of freedom B bar, right? So B bar, the global degree of freedom, were lucky enough to find itself on one of the Neumann degrees of freedom, right? The degrees of freedom on which we have Neumann boundary conditions specified. Then we would have here F J element EI contribution from local node B plus F EJ contribution from local node D. Just note that the J that I'm using here is just a superscript to indicate to us that that this contribution to the forcing comes from the Neumann boundary condition that we're denoting as J, that we're writing as Jn. Okay, so the same thing would carry on. Okay, all right. So that's how we would assemble these global matrices and vectors that go into our global finite element weak form, right, in matrix vector form.